Hello, my name is Sripati Arasi. My colleague Easy Zhang and myself, we work in Dell Computers. The title of my talk is Modeling of a Notebook Antenna using CST Microwave Studio. The agenda of this talk is first a brief comparison of CST with other electromagnetic simulation tools that I have used in the past for mobile phones and for other devices. Without going into the company confidential proprietary, I have used a Dell notebook as a benchmark by importing the ProECAD file into the CST simulation tool. A 4 antenna model was used to evaluate the antenna performance, and then, as you know, mesh is a very important factor in governing the effective use of any simulation tool. So here also we'll talk about the mesh of the Dell notebook with respect to the CST simulation tool. And then after importing the Dell notebook by using a ProECAD file, we selected the material parameters, we assigned the boundary conditions, and we ran the model, and then we calculated S parameters, radiation patterns. So all those results will be shown, whatever that I can show without contradicting my company thing. And then I'll give some feedback on the type of phantom head and phantom hand model that is used for laptop, which is somewhat different compared to the mobile phones. And finally, some of the systems like desktop and laptop that should be used so that your simulation can run very nicely. Here, just to give a very brief comparison of the CST method with the other simulation tools. Frequency domain like HFSS based on FET, finite element theory, is fairly accurate, and it gives very nice results. But as the parts are increasing and as the structures become very complicated with lot of curvatures, then it becomes very time consuming because we have to solve each and every tetrahedral mesh cell. So one way to make a quick and a reasonable approximation is by using a staircase method like XFTD or SEMCAD. It is a reasonable approximation, but sometimes it's oversimplified. Just to give an example is, for example, this is a coarse mesh. This is a coarse mesh 50 ohm part. When you applied the staircase method by using coarse mesh, then it gives like 44 ohm. That is a 6 ohm error. Now, if you want to have a very accurate 50 ohm for that part, then we have to use an extremely fine mesh as shown here. So that means you are again increasing the time even by using staircase mesh. So the only way staircase mesh can work, the only purpose it can work is for a very quick solution. Now CST is based on PBA, their own patented PBA. So I'm not going to tell all the details of the PBA because it's their property. However, just to give an idea what PBA and how it compares with other tools is, PBA, perfect boundary approximation, where the field sampling is based on the mesh density. So here, as you see, even in the curvature, there are mesh cells that are accounted for. So what happens is, when you account even in those mesh cells too, even a coarse mesh will give as accurate simulation parameter as the fine case in the case of staircase mesh. So this is what I felt very advantageous with the CST in using, that is, your accuracy is not lost just because you're going fast. So here a Dell notebook was used as a benchmark by importing, this is a generic Dell notebook which is already available in the market. So we imported this in the simulation tool, and usually a step format I found is better to use instead of a SAT format, because when you import a SAT format CAD file, the names are lost, whereas if you import a step format, all the names are retained. So this way you know which component is which part. Then before going to this frequency ranges, long back when the laptops were started, only Bluetooth antenna was present in that. But now things have dramatically changed. First, any laptop, if you take, it has a wireless LAN antenna. That too not just one wireless LAN antenna, it has multiple, one or two. And here, this antenna frequency range spectrum, each color represents one frequency band. For example, First, let me tell about the WLAN. WLAN, as you know, is for Wi-Fi spots. So if you want to go for 802.11a, so you're in this 2.4 gigahertz range, and if you want to go for 802.11g is in this range, and 802.11a is in the 5 gigahertz range. And now we are also adding MIMO so that you can also use 802.11n. Now, apart from that, the wireless LAN antenna, nowadays we are also putting WiMAX feature so that it can be used for any far range. So WiMAX frequencies are like 2300 to 2400 and also 2500 to 2700 megahertz range. So that is just 3 wireless LAN antenna. Usually WiMAX is for main and aux. MIMO we normally don't put that. Then in order to have a mobile broadband, like if you are using Verizon or AT&T, then we have to use this WWAN, wireless wide area network. So that frequency range goes from like 824 to 960, this color, and to 1710 to 2170. That is, it is covering GSM 850, GSM 900, GSM 1800 and UMTS range, so that all carriers can use it. And it also has a GPS. Then apart from this, now the laptops we are going to put like UWB, like a wireless USB, so that like a docking station, so that suppose you want to run some video, you can just wirelessly stream all the videos. So that is UWB. And in the UWB also, initially it was only band group 1, but now we are also going for band group 3. The reason in the just to give an idea for the people who are away from UWB, we don't use band group 2 in UWB because band group 2 interferes with the wireless LAN frequencies. Wireless LAN frequency. So when you are using so many antennas, and if you start hand prototyping these antennas without doing simulations, then the antenna designer will face a lot of problems. So one of the ways to use simulation. So because I cannot show all the antennas, so what I did as an example, I took 4 antennas on the display, so they were placed. So these most of the time we put antennas on the top of the display. That is, pretend this is the laptop. So most of the antennas we try to put it on the top so that the radiation pattern is all over. Here, so as you can see, is behind this bezel. So it's behind this bezel the antennas are placed. So the different types of antennas also you can make. You can make a stamped metal. You can also make insert molded. So, but here just to give an example, we made different types like IFA, helical coil. This in the bottom, as you see, we have removed the plastic just to show where these antennas are present. But in mobile phone, most of the people are now aware that you have this antennas which is quarter wavelength, and you use the ground plane as the image. So you have quarter wavelength and the image quarter wavelength, so it's half wavelength, and it works very fine. So that is, the ground plane also acts as a part of the radiator. But in laptop, the scene is not that good, because the ground plane, if you take this is the magnesium frame. Most of the laptops, sometimes they have a magnesium frame, or you can use the LCD display. This is all metal. Now this metal is quite big, bigger than quarter wavelength, so it cannot function like a ground plane. It's not like a part of the radiator. In fact, it's more like a reflector. So what is there? Then you use cables, lengthy cables, to go all the way to the motherboard on the. So you can see the cables coming here, antenna 1, 2, 3, 5, 6. So going all the way to the. So the cable can run as much as like 350 to 700 mm. So the best way to use the feeding, if you want to use a simulation for the laptop, is by using waveport method. That is, actually you can even, by using simulation tool, you can even make your own cable like this one. Jeremy has helped me in making this cable, and you can apply all the properties, and then you can use that. But in this case, what I did is just to have a quick simulation for the 4 model, I used a discrete 2-port method, which is a lump port method, and then I just added the cable losses for each antenna. So these are this discrete 2-port method, wherein you select 2 points and you feed the antenna. And so these are the 4 ports, as this red circle indicates the ports. And this is the mesh view of the antenna. What what is there, as I said, mesh is a very important parameter in governing the effective use of the simulation. If mesh is not properly placed, that means the simulation is not correct. So one thing I liked in CST is you can take you can put all the components. You don't have to actually eliminate all the components. And the way to do is there is a priority in the, so you can prioritize the meshes. Some components which are secondary, like keyboards, all the keypads and all the things on the bottom, they are like secondary, so you can put secondary priority. And the antennas, magnesium frame, and the flex, you can put all like a primary. And so this way you can solve your antennas and all the in the presence of all other things. So the notebook parameters are once again just like mobile phones. You need to find for the low VSWR, you want high isolations, and you normally measure three-dimensional antenna performance for wireless wide area network, and then two-dimensional for, because you want wireless LAN antenna. And the reason wireless LAN antenna you want to do the two-dimension is because when the radiation goes, you want to go that side, you don't want to go down towards the laptop, because what is this is the LCD display, it has a lot of components, and if the radiation goes down, it creates RF noise, and the electronic components cannot function well. So that's the reason the polarization is very important. The vertical polarization plays a very important role in the UWB antenna, and of course RF noise should be low, so antenna engineers should also take care of the RF noise. Throughput is like a data rate, so once you put this laptop, you want to see how much data rate it's communicating. For that also vertical polarization is very important. So all that while designing the antenna, we have to look at it. So simulation tool comes extremely handy. So as I said, several types of antennas that were used, even in this one: helical coil, split helical coil, simple monopole, PIFA, IFA. So here I just taken one simple IFA as an example for the antenna phase simulation. In IFA, just to give an idea, is in IFA this length, it is called IFA, means inverted F antenna, and the name comes because of the shape. So this length controls both the performance and also where the antenna is tuned. And this feed and the ground post, if you look at it, you can say model this feed like one inductor, and this ground post one inductor. So that means two inductors, they are placed side by side, they act like a secondary transformer. So the distance between them can control the matching, how well the antenna is matched. And the distance between the magnesium frame and the radiator, that controls the performance. Usually 10 mm is good, but when you're working with mechanical and ID people, where they are crushing the dimensions, even getting 7 mm is very hard. So this antenna was simulated after assigning the material properties based from the CST database. It's not that of course you can also measure your own property, but what I've observed is whatever the material database that is there in the CST, pretty close to what is available in the standard literature. So you can as well take the material property from the database and assign it. Then you have to of course assign the boundary conditions for each component. And so when we calculated this for a WWAN diversity, which also has a GPS antenna, and it came pretty close, but of course it needs some retuning in both the lower and the higher band, but we felt it came pretty close. And in the GPS it was perfectly tuned at 1575. So we calculated the radiation profile and the antenna efficiency of the GPS antenna. As I said, even for whether it is for WLAN, particularly for GPS, you want the radiation to go up so that the satellite can detect. It's a receive, right? So as you see the radiation pattern from here, most of this red indicates the peak radiation here. So most of the peak radiation is on the top, and only very little radiation is going down. So that means it's very good, it doesn't create any noise. And then we calculated the radiation efficiency, which was coming 49%, which is very close to what we measured actually in our chamber. Then there is one more thing is in the laptop, this as I said, Bluetooth, wireless LAN, they pretty well share the same frequency range. Now you are also adding WiMAX to the wireless LAN. So what happens, there is a coexistence of Bluetooth. If you put Bluetooth wireless LAN antennas just on the top of the display, then there is a coexistence problem, and so you need a very high isolation in order for your WiMAX to work. So what initially when we put Bluetooth and wireless LAN on the top, and we were getting very low isolation, sometimes even 10 dB. So we started swapping the antennas back and forth, and despite all that, the isolation wasn't improving. So well, what I did is we ran CST simulation and tried to see if by swapping antennas within the CST simulation if we can get better. And there also the maximum we were getting 18 dB. So this indicates that we shouldn't even put Bluetooth very close to wireless LAN anywhere on the top if at all you want WiMAX to work. So we moved the Bluetooth to the base. I could have shown that particular result too of how by moving to the base how the isolation improved, but because it's just a company thing, so I didn't bring that here. But well, what I'm trying to say is here the simulation will help also in reinforcing our idea whether we are doing anything wrong in our antenna prototype. This is like what is that to peak field. What happens is whenever this antenna is radiates, some of the radiation goes down. So as I said before, there are all electronic components inside the LCD display, and you want the noise come from two places. One is a conductive noise, other is a radiated noise or near field noise. So what happens, the near field radiated noise comes from the antenna, so we want to put thick EMI absorbers here to reduce the noise. But how thick should we put? We cannot start just randomly putting some EMI absorbers. So what is this also it's not like a RF noise parameter, but I'll see if this works here. Yeah, you can see the radiation goes down. So here there is no EMI absorber, so that means it's going all the way to this area. So any components in this area can be damaged. So that means we can put EMI absorbers here and again do the simulation to see how much we can control the RF noise. Sorry. This is like an academic purpose study, but it's very good for mobile phones, for laptop or anything. What is there? As I said, a laptop has some, not all laptops will have, but a good number of laptops has a magnesium frame. The reason they use magnesium frame is because it's steady, so the laptop when it falls it won't break. And if you use a magnesium frame and if you use antennas on the top, it's going to damage. And also what is there, sometimes people want to make a magnesium frame and plastic by one piece, that is you insert mold plastic in a magnesium frame, so it's just one piece. And then then we were trying to see how much the magnesium frame is going to damage. So each property was studied, like so we put just a surf cover, that is just a cover, and then a plastic molding, and then just magnesium, and trying to see the VSWR. So this way we can also use the simulation tool for the academic purpose of the effect of each material. So here we have used this to make an insert molded plastic on a magnesium frame. And this is about the SAR. Initially SAR in laptops was something not known. It was more like a formality, and sometimes people were not even aware that FCC requirement is too big deal for. The reason is, what FCC requirement is, antennas should be 20 centimeters away from the user. As long as it is that, you are pretty well done. This is as simple as that. But now laptops are changing. As you know, we are getting like a tablet mode wherein you can do and put it down, like this case. So what happens, these antennas are now coming towards the user, like 5 centimeters or even less than that. And sometimes even you're using hand on the. So now it's FCC is not a formality, it's more like a requirement now. So we have to do all the tests. Well, what I've observed when I wanted to do the simulation using this one is, most of the simulation tool is like you have a phantom head like that is used in mobile phones. You put it in mobile phones, what is there, you do a two-touch method and you do the SAR. But here the case is different. For example, this is display open, wherein the laptop is here and the probe touches here and measures. So and in this case it's a tablet mode in which it swirls around, and then you measure with the probe about the SAR. So in this case, so one of the things that we need from the simulation tool is a kind of a phantom model that can be used even for laptops, so that we can even measure SAR for the laptops. So that will be the future studies that need to be addressed from the simulation perspective. I'm not sure if it is there, but I couldn't find. So maybe we'll see if there is an improvement in that one and that particular aspect. And what type of systems that can be used so that your system doesn't crash while you're working. Well, one is what I've observed, we can use a precision workstation. Earlier there used to be a precision 690, but now there is a even advanced one. In fact, 690 now replaced with a higher power one like T3 500. It's a 64-bit operating system, 8 GB RAM. If you use that, it's like a monster and just runs a simulation very fast. And there is another advantage by using Dell Precision system is it has like a feature wherein you can put this hardware acceleration card, and also the cluster inbox made by the CST with somebody, they're like a 2 acceleration cards, so you can actually remove it and put 2 acceleration cards and make software run very fast. This is for the desktop. But if you want to use laptop, you're on mobile and you want to use laptop. So there are also some laptops, the same thing. They're all called as Dell Precision, whether desktop or laptop. In the laptop, it is Dell Precision M6400. I've used this one using CST, and this is just like a picture to show from marketing perspective that how tiny things you can run like a ProE file. So this is and you can work this also, like it has a 2 dual core and up to 16 GB, very fast. So see, it also has a 64-bit operating system. So and apart from that, it also has a mobile broadband, as I was telling you. So that is even while you're in the airport, you can do simulation if you want. So that's all. Thank you very much for that. Okay.
Any questions here for Patrick?
Yeah.
Did you get a chance to do any radiation pattern type measurements to compare your simulation results?
Yes, for the GPS we have done. For the GPS, yes. For wireless LAN also we have done. For wireless LAN, yeah.
How was the comparison?
Comparison for GPS it came out very good. For wireless LAN, it was okay. It wasn't too bad. It was okay. Just slight comparison. Yeah. That may be because I didn't use all the components in my simulation, whereas in the reality in the laptop we have all the components. So like there are a lot of electronic components that I didn't put, so that might have played a role as well in wireless LAN. But in the GPS it was pretty close. Yeah.
Similarly, you are commenting on your need to have your radiation efficiency very, very high and noise very low.
Yeah.
Are you also able to verify that?
Yes. The for GPS 50% came out very accurate for the GPS. But wireless LAN, what is there because of the very wide frequency range, and whereas the antenna that we had was not high bandwidth, so there was some discrepancy. But wherever that was essentially it wasn't tuned well in the simulation compared to the prototype. But wherever it was, when I removed the mismatch loss, it was okay. Yeah.
Anything else? Okay, well, thanks very much.
Yeah, thank you.
Very nice presentation.
Yeah.
So now I want to introduce Carl Baldwin.